Welcome to the APL quest. See APL Wiki for details. Today's quest is the first from the 2016 round of the APL problem solving competition. We are simply to compute the mean, or arithmetic mean, the average. There are a couple of gotchas here, but for the very basic part of the problem, this is extremely simple. Now, the mean is defined as the sum divided by the count. So we could define the parts of the mean and then combine them for the whole thing. And we could do that like this. We can define small lambda functions in APL using curly braces. Inside the curly braces, the argument is denoted omega. And then we need to actually compute the sum, and we do that by inserting plus between the elements, also known as reducing using plus. So this is plus and this is the reduction, and this function then sums. Let's define. So this is a list, or a numeric vector, and we can sum the numbers like this. Now we want the count, and there's actually a built-in function for the count in APL. It's also known as tally. That's why it looks like a tally mark. Next, we can combine these. So here we define a mean function, and we want the sum of the argument divided by the count of the argument. Now, I put parentheses on the left here, and I didn't put parentheses on the right. And this is because APL's order of execution is such that any function, these functions for example, and also built-in functions, every function, takes as right argument everything to its right as far as it can see until it gets stopped by, say, the end of the expression or the end of a parenthesis. Whereas as left argument, it only takes what's immediately to its left. So we need to make sum take as argument just the right argument to this outer lambda. But we want count to take as argument this other argument, and then the right argument to the division function should be everything to its right. So that's the entire expression on the right. That's the count there. So we could parenthesize as well the count, but we don't need to. We do need to parenthesize the sum of the argument, because otherwise, without this, what sum would take as argument would be everything to its right. In fact, it would give the same result because we would be dividing all the elements by the count first and then summing them, but that's less precise and not as performant either. Okay, so now we've defined the mean, and we can apply the mean to P, and we get the mean of these numbers. But there are some notational niceties we can do in APL as well. There's something called tacit programming, or points-free programming, which basically just is a fancy name for meaning I'm not going to mention my arguments. So here we have a mention of the argument, and over here we have another mention of the argument. And basically what happens if we go tacit is that we express everything in terms of functions. So we have the sum function applied to the argument divided by the count function applied to the argument, and this can also just be expressed as the sum function divided by the count function. So we can get rid of a lot of noise. We don't even need the outer braces anymore. That's the indicator that we're going to use the argument name, and so we can write it just like this: the sum divided by the count. And so these two outer functions are applied to the argument, and the middle function is applied between their respective results. And the function still works. what's interesting here is that we've defined sum and count. In fact, we could redefine them as tacit functions as well. So we can redefine sum. We defined it as the plus reduction of the argument, but again we're mentioning the argument, and we could omit the mention and remove the braces. So we could write sum like this, and we could write count similarly, just like that. And then we can redefine mean in terms of these new sum and count, and it still works. Of course, this is a bit ridiculous. Why would I give a name sum to something that's shorter than the name itself? Sum is 3 characters, and we probably can't really find any name that would be as short as 2 characters, which is the definition of sum. Count here is 5 characters, but we only need 1 character to express it. So we could just take these values and substitute them in to our definition for the mean. So we could just write the sum divided by the tally, or the count. And then we can compute it like that. In fact, we don't even need the spaces. So the entire mean definition can be written like this. 4 characters. At which point you might then question, why would you even bother calling the function mean when you could just use the 4 characters that means the mean, and then everybody can see exactly what it means. Anyway, this is a short way of defining the mean. And there's a problem, and that is that the problem specification, you can look there, says that this also has to work on the empty list. And if we try that, so we have a symbol for the empty list, which is called tilde, because it is a combination of a 0 and the character tilde, and you pronounce them together as tilde. It basically means there are no numbers. It's an empty list like that. So we can see that this means, this picture here means that it has a single axis. The axis has no elements, and when we have it being numeric, this means the type is numeric, and this is just an example of what such an element would look like. It would be a 0 if there had been elements there, but there aren't any. You can kind of see the 0 tilde thing. Now, if we try to do the mean of the empty list, we get 1, which might be a bit mysterious. But what's actually happening here is that when we sum it, we get 0, and when we count how many elements there are, we also get 0. And 0 divided by 0 is traditionally defined not as an error, but as 1 in APL for consistency, such that all numbers divided by themselves give 1. However, in this case, that's not very good. We want the problem specification says it has to give 0. So we can fix this, because we have only in the case where there are 0 elements, we get the sum divided, which is 0, and then divide by 0, which makes it too big. But if we were dividing by 1 instead, then we have 0 divided by 1, and then that would give you 0, and that's the result that we want. So we can fix this by taking the maximum of 1 and the count. So if the count is 1 or more, then it doesn't make a difference. And if the count is 0, we get 1. So we basically clamp it to become 1 or more. And how can we do that? Well, if we go back again to our very verbose definition of the mean, where we had, and let's now substitute in here, the sum of the argument divided by the count of the argument. Well, then we need a maximum function, which we have in APL. It's denoted by the up style. And you can kind of see that it's like this vertical bar, and then it has a bar at the top indicating that we want the maximum. Correspondingly, the minimum would be this. It's a vertical bar with a indicator at the bottom. But now we want the maximum. And then we can put in a 1 over here. And keep in mind the order of execution in APL. Every function takes as right argument everything to its right as far as it can see. So maximum here takes the count of the argument, the omega, as its right argument, and its the left argument is to its immediate left. So that's just this one. division takes the result of this entire expression on its right. And now mean works as before, but if we do it on the empty list, we get 0 as required. But we can actually do this tacitly as well, again in terms of just function application on the argument. So here we have the count, and then we do the maximum of 1 and the count. That still works like that. And then we have a division, and what we want to be divided is the sum. So this says the sum divided by 1 maximum count. And the count we can again substitute in here. And this gives another, again, we could remove spaces if we wanted to. And this gives us the mean which works on P, and mean which works on the empty list. And this is a very good solution to the problem. And let's just demonstrate some features of it, because actually the problem wants us to make this applicable even to higher rank arrays. So APL arrays are not just lists of things, but they're actually multidimensional. They can be arranged along multiple axes. Let's define a second number. So now we have P and we have Q, these two lists. And they are one-dimensional. There's only one axis that can be collapsed by taking the average over that axis, but we can combine them in various ways. And one way to combine them is to combine them into a table or a matrix of 2 columns. And we can do that by making each one of them into a 1-column matrix, or a column vector, also known as that, and then concatenate them together. So we have this function, comma bar, which is called table, and it takes an argument, say Q, and it makes it into a matrix. So here this arrow indicates that there's a single axis along which the elements are ordered, and here we have 2 arrows which says that there are 2 axes along which the elements are ordered. So this is the first axis, which are the rows, and the second axis, which are the columns. And we could of course do the same thing for P. And then we could combine the 2 of them with concatenation. So we can take the table of P concatenated with the table of Q. Again, I don't need parentheses on the right because the concatenation function takes everything on its right as its right argument. And now we have a 2-column table. We could actually write this in a much neater way, because what we can see a symmetry here. We see that we are concatenating the tabling of these 2 arguments, P and Q. And we have a way to write that in APL. We can write P and Q concatenated with each other, but we don't want to concatenate the P and the Q. We want to concatenate a certain aspect of P and Q, namely their table form. And for that we use what we call the over operator. You could see this as pre-process the arguments as in a certain way. And so this is not a function. This is called an operator. It's a higher order function. It takes the concatenation on one side, and it takes the tabling on the other side. So these are 2 functions, and it combines them into a new function, which isn't concatenation. It is the concatenation of the tables. So this does exactly the same thing as the previous expression we wrote. It does a table on each one of them, and then it concatenates them together. And so with this new array, which we can call A, we can take the mean of A, and this gives us a 2-element vector or list, 1 per column. And why is it doing the average vertically, so to say? Because the tally counts along the leading axis. How many elements or subarrays are there along the leading axis? And so for both of these, and it couldn't be otherwise, it can be ragged, there are 5. And also the summation that we did, which was the plus reduction. So this was the reduction symbol, which actually also isn't a function. It's an operator, higher order function, which takes this plus and modifies this, much like the over operator modifies the concatenation, modifies plus to become a plus reduction or a summation. And this also works along the leading axis, which is over here. So we're summing each column, and then we have the 2 column sums. We can try this. And then we're dividing by the tally of the number of rows, and that's why we get the 2 averages. APL automatically pairs up elements of arrays when we're doing arithmetic. So 2.8 and is the result of 14 divided by 5, and 3.2 is the result of 16 divided by 5. What if we wanted to sum and count along the rows? Well, then there's another operator, a higher order function, that we could use to modify a function. And it's not just built-in functions that can be modified. Even our own function mean can be modified. So we count the number of dimensions. This has 2 dimensions, this whole thing, but each row in itself only has 1 dimension, and we want to apply the mean function not to the entire table, but to the one-dimensional subarrays of this table. And for that we have this, which is called the rank operator. It takes this function on the left and then a specification of the dimensionality or rank of the argument that we want this mean function to see. And so this says the mean on each subarray of rank 1, that is on each row. And if we do that, then we get 5 results. So 2 is the average of 3 and 1, and 3.5 is the average of 1 and 6, and 2.5 is the average of 4 and 1, and so on. And so this, by defining a function in terms of the leading axis, this allows us later to also have a function available that we can apply on other axes simply by using this rank operator. And that's all I wanted to show for today. Thank you for watching.